Imagine standing at the edge of everything we know. Behind you, the light of 1,000 discoveries. Before you, an endless darkness filled with questions that no one can yet answer. That darkness is not frightening. It is beautiful. Tonight we journey into the unsolved mysteries of science. There is no test waiting at the end. No rush. No urgency. Just the slow unwinding of cosmic puzzles to carry you gently towards sleep. For every answer science has found, 100 new questions have emerged. The universe is not a book of final truths, but an endless story still being written. Tonight we explore the boundaries of human knowledge. From the nature of consciousness to the fabric of space-time. From the origin of life to the fate of the cosmos. All of it waiting to be whispered into the quiet of night. Tonight, let's drift off together while exploring over 100 calming mysteries that science has not yet solved. There's no rush here, no test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I'm glad you found your way here tonight. Perhaps you've had a long day, or maybe you simply enjoy falling asleep to thoughts that stretch beyond the limits of what we know. Either way, this journey is for you. There is something profoundly peaceful about contemplating mystery. Each unanswered question reminds us that the universe is vast enough to still hold secrets. That wonder is infinite, that there will always be more to discover. So settle in. Let your breathing slow. And let the weight of the day drift away like starlight across the endless dark. The greatest mysteries are not problems to be solved, but doorways to be appreciated. They remind us that we are explorers in a cosmos far greater than we can yet comprehend. Tonight we will wander through these mysteries together. We will ask questions that have no answers yet. And we will find peace in the not knowing. But there is no hurry. These mysteries have waited for centuries. They can wait a little longer while you rest. Let us begin with the deepest question of all. We still do not know why there is something rather than nothing. This is the most fundamental mystery imaginable. Why does the universe exist at all? Why is there something instead of nothing? Physics can describe how the universe behaves once it exists. Cosmology can trace events back to the very first moments after the beginning. But why there is a universe at all, why there are laws that permit it to exist, remains unanswered. Some physicists suggest that absolute nothingness may be unstable. That something must always emerge from the void. Others propose that our universe is one of countless others, each bubbling into existence with its own laws. But even if these ideas are true, they only push the question deeper. Why should there be a multiverse? Why should nothingness be unstable? Perhaps the answer lies beyond the reach of science. Perhaps it is a question that cannot be answered by any method we possess. Every star, every atom, every thought you have ever had exists upon a foundation we cannot explain. The fact that reality is here at all remains the deepest mystery we face. And somehow, that mystery is calming. It reminds us that existence itself is a gift. Unexplained, unexpected, but undeniably here. We do not know what triggered the Big Bang. Cosmologists have pieced together a remarkable history of the universe. They have traced events back nearly 14 billion years to a time when everything was compressed into an unimaginably hot, dense state. We call this beginning the Big Bang. But what actually caused it remains unknown. Some theories suggest the Big Bang was a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time themselves. Others imagine it as one moment in an eternal cycle, with universes expanding, collapsing, and beginning again. What makes the question even stranger is time itself. If the universe includes the birth of time, then asking what came before may not even make sense. There may have been no before. Our telescopes can see the universe as it was in its infancy, but they cannot peer into the first instant itself. The true first cause remains hidden. The cosmos burst into being, and no one knows why. The arrow of time points only in one direction, but we do not understand why. Every moment, the present slips into the past. We remember yesterday, but not tomorrow. A broken glass never leaps back together. Heat flows from hot to cold, never the reverse. Time flows forward, always forward. This is called the arrow of time. What makes this strange is that the fundamental laws of physics do not require it. At the smallest scales, particles can move forward or backward in time with equal consistency. The equations are symmetrical. So why does our world insist on moving only one way? Scientists often connect the arrow of time to entropy, the tendency for disorder to increase. The universe began in an exceptionally ordered state and has been running down ever since. But why did it begin that way? Why should the cosmos have started in such low entropy that time could even have a direction? Some physicists think the arrow emerges from how information spreads. Others suggest it is tied to cosmic expansion. But no explanation is complete. Time's direction is something we live inside every moment. And yet why it flows forward, and only forward, remains a haunting mystery. Most of the universe is made of dark matter, but we do not know what it is. When astronomers measure how galaxies spin, they find something strange. Stars at the edges move far too quickly, as if held by an invisible force. By all logic, those stars should drift away into space. Instead, they remain bound. The conclusion is inescapable. Most of the mass in the universe is invisible. We call it dark matter. It does not emit light. It does not absorb light. Telescopes cannot see it directly. Yet we know it must be there, because its gravity shapes everything around it. Dark matter holds galaxies together. It bends the paths of light from distant clusters. It leaves faint ripples in the cosmic web. What is it? Scientists have searched for decades. Some think it consists of undiscovered particles. Others suggest primordial black holes formed moments after the Big Bang. Experiments buried deep underground wait for a passing dark matter particle to collide with a single atom. So far, none have. This invisible substance is 5 times more abundant than ordinary matter, and we have no idea what it is. Dark energy is pushing the universe apart, and we do not understand it. In the late 20th century, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is not slowing down. It is accelerating. something is pushing galaxies apart faster and faster. Some unknown energy is embedded in the fabric of space itself. We call it dark energy, though the name is only a placeholder for our ignorance. Dark energy makes up nearly 70% of the entire cosmos. Yet we do not know what it is. One idea suggests it is a property of the vacuum, a constant energy present in empty space. Another possibility is that our understanding of gravity is incomplete. What makes the mystery even more unsettling is its consequence. The universe's fate depends on this invisible force. If dark energy remains constant, galaxies will drift apart until only empty darkness remains. If it grows stronger, it could eventually tear apart stars, planets, and even atoms. We can measure its effects, but we cannot see its true nature. Dark energy is the unseen hand, shaping the ultimate future of everything. We do not know why the laws of physics seem tuned for life. The universe appears balanced on a knife's edge. If gravity were slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form. If the electromagnetic force were different, atoms would not bind together. Tiny changes to the constants of physics would make life impossible. This puzzle is called fine-tuning. Why should the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or nuclear forces to take the strengths they have. Some argue this is merely coincidence. Others suggest countless universes exist, each with different laws, and we simply live in the rare one where life is possible. Another idea proposes that there may be a deeper principle, still undiscovered, that forces the laws to take these exact values. For now, we cannot say. But when we look around at stars, planets, and the fact that we can even ask this question, we are reminded that the universe seems uncannily suited for life. And why that is so remains one of science's greatest mysteries. We do not know whether the universe is finite or infinite. The observable universe is vast, about 93 billion light-years across, but we cannot see beyond it. Light has only had so much time to travel since the beginning. What lies beyond that edge? One possibility is that the universe extends forever, stretching endlessly in all directions, with no boundary at all. If so, space may contain an infinite number of galaxies, stars, and perhaps even other worlds like Earth. Another possibility is that the universe is finite, but unbounded, like the surface of a sphere. Travel far enough in one direction, and you might eventually return to where you started. Scientists search for answers in the cosmic microwave background, the faint afterglow of the early universe. Its patterns might reveal the cosmos's true shape. So far, the evidence suggests the universe is very nearly flat. But this does not settle whether it is infinite. The true size and shape of reality remains hidden, just beyond our reach. We cannot observe most of the universe because it lies beyond the cosmic horizon. The most distant galaxies we can see are over 13 billion light-years away. But beyond them lies a region forever hidden from view. This cosmic horizon is not like a physical wall. It is a limit set by the age of the universe and the speed of light. Beyond it, reality continues. But we can never know exactly what is there. Perhaps it is much the same as what we see. Galaxies, stars, and planets stretching far beyond our sight. Or perhaps it is radically different. Some theories suggest our observable patch is just one bubble in a much larger reality. If true, the vast majority of the universe lies forever beyond what we can measure. We are bound within a cosmic island. The sky we see is only the smallest fraction of what may exist. The rest is out there, silent and unreachable, a permanent unknown. Some scientists believe other universes may exist, but we cannot prove it. The idea of the multiverse is one of the boldest in modern science. It suggests our universe may not be unique, but one of countless others. Each universe could have different laws of physics, different histories, even different numbers of dimensions. This concept arises naturally in some theories. Inflation may create bubble universes, each budding off with its own conditions. String theory predicts a vast landscape of possible realities. The multiverse could even explain fine-tuning. We live in a universe suited for life, because only in such universes can observers exist. But there is a problem. If other universes exist beyond our cosmic horizon, we may never observe them. No light or signal could ever cross the boundary. This makes the multiverse both fascinating and controversial. An idea we cannot test may never be more than speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most intriguing mysteries in physics. Space and time may be made of deeper structures we have not discovered. Einstein showed us that space and time are not fixed backdrops, but flexible and dynamic. They bend, curve, and stretch, shaping the paths of planets and the flow of light. But at the deepest level, what is this fabric made of? At the smallest scales, relativity and quantum mechanics clash. Space and time seem smooth in relativity, but quantum theory suggests everything should be grainy, fluctuating, and uncertain. Some ideas propose that space and time are not fundamental at all. Instead, they may emerge from something deeper, perhaps a network of quantum information that gives rise to geometry. In this picture, space-time is like a surface, and underneath lies a more basic reality we cannot yet see. Others wonder if time itself is even real, or if it is an illusion created by deeper processes. Space and time feel like the stage upon which the universe unfolds. Yet the stage itself may not be what it seems. A single particle can exist in two places at once, and we do not understand how. Quantum mechanics tells us that particles do not have definite positions until we measure them. Instead, they exist in superposition, a kind of probability cloud where many outcomes are possible simultaneously. An electron can be here and there, passing through both slits of an experiment at once, interfering with itself like a wave. Only when we observe it does the particle seem to choose a single location. This is not just theory. Experiments have confirmed superposition with particles ranging from electrons to molecules thousands of times larger. Does the particle physically exist in two places? Or is superposition merely a reflection of our incomplete knowledge? Some interpretations suggest multiple realities branch at each measurement. Others propose reality itself is fuzzy until observed. Whatever the answer, the ability of a single particle to seemingly occupy two places remains one of the strangest mysteries of modern science. Entangled particles remain connected across any distance, and we do not know why. When two particles become entangled, their properties link in a way that defies distance. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, because it seemed to violate the cosmic speed limit. Nothing should move faster than light. Yet experiments confirm entanglement is real. Particles have been entangled and separated by hundreds of kilometers. The correlations remain perfect. It is as though nature keeps a hidden ledger, ensuring outcomes stay in sync. Some physicists suggest reality is non-local, woven together more deeply than space and time allow us to imagine. Others think entanglement points to hidden variables we have not discovered. We use entanglement in quantum computing and secure communication, yet we cannot say why it works. The universe whispers across distance, and we still do not know how. Observing something seems to change what it is, and no one knows why. One of the strangest discoveries in physics is that measurement affects the system being measured. In the famous double-slit experiment, particles behave like waves when unobserved, creating interference patterns. But if we measure which path they take, the wave-like behavior vanishes. The outcome changes simply because we looked. Why should this be? One explanation suggests the wave function, the mathematical description of possible states, collapses into a definite outcome when observed. But what counts as an observer? Is it a measuring device? Human consciousness? Or is collapse merely an illusion hiding deeper laws? Some interpretations say every possibility happens, branching into multiple universes. Others suggest particles only become definite when information about them spreads irreversibly into the environment. None of these ideas have been proven. The line between observer and observed is not as simple as we once believed. The universe seems to care whether it is being watched, and no one knows why. Gravity is far weaker than every other force, and we do not understand why. Gravity rules the cosmos. It holds planets in orbit, shapes galaxies, and governs the motion of stars. Yet compared to other forces, it is remarkably feeble. A small magnet can overcome the gravitational pull of the entire Earth. The electromagnetic force, strong nuclear force, and weak nuclear force all operate with enormous power at tiny scales. Gravity, by comparison, is barely noticeable. Why is there such an imbalance? One possibility suggests gravity spreads into hidden dimensions we cannot see, diluting its strength. Another proposes that gravity's true scale is strong, but masked by unknown physics. Despite centuries of study, we still do not understand why gravity is so much weaker than other forces. This weakness is not merely a curiosity. It is fundamental to cosmic structure. Without it, stars and galaxies could not exist. The gentleness of gravity is a quiet mystery that makes the cosmos possible. Einstein's universe and the quantum world both work perfectly, yet they refuse to fit together. General relativity describes the cosmos with unmatched precision. Quantum mechanics explains the microscopic world with astonishing accuracy. Each theory has passed every experimental test we can devise. But they do not agree with each other. When we try to describe situations where both matter and gravity are quantum, like inside black holes or in the first moments of the universe, the equations break down. Infinities pile upon infinities. Physicists have searched for decades for a theory of everything that unites them. String theory and loop quantum gravity offer tantalizing possibilities, but no experiment has confirmed them. The fact that our two most successful theories describe different realities is one of the greatest paradoxes in science. Both work perfectly, yet together they fail. The heart of a black hole remains unknowable. Black holes are regions where gravity is so strong that nothing, not even light, can escape. As matter falls inward, it is crushed toward the center. According to Einstein's equations, everything collapses into a single point of infinite density, a singularity. But infinity is usually a sign that our mathematics has failed. What truly lies at the heart of a black hole? Some think the singularity is real, a place where known physics breaks down. Others believe a deeper theory will replace it with something we cannot yet imagine. We cannot see inside. The event horizon hides the interior completely. For now, the heart of a black hole remains sealed away, beyond observation and beyond certainty. It is one of the most inaccessible mysteries in science. We do not understand what happens to information inside black holes. When matter falls into a black hole, it seems to vanish forever. But physics says information, the details about any system, should be preserved. So what happens to it? Stephen Hawking showed that black holes slowly evaporate through radiation. But if they vanish completely, where does the information go? If it is destroyed, fundamental laws would be violated. If it escapes, somehow it must leak out through the radiation in ways no one fully understands. This puzzle, known as the black hole information paradox, has challenged physicists for decades. Some think information is stored on the event horizon itself. Others suggest black holes connect to other regions of space-time. The fate of information in a black hole touches the deepest foundations of reality. Hawking radiation is predicted but never directly observed. In the 1970s, Stephen Hawking made a stunning prediction. Black holes are not truly black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass. This Hawking radiation is one of the most famous predictions in modern physics. Yet we have never seen it. Real black holes are surrounded by hot gas and violent environments that overwhelm the faint trickle. Detecting it directly may be impossible with current technology. Laboratory experiments have tried to create analogs using sound waves and fluids, but these remain indirect hints. Whether Hawking radiation truly exists remains unproven. If it does, it will reshape our understanding. If it does not, something even stranger must be happening. The origin of life on Earth is still unknown. Life began more than 3.5 billion years ago. Fossil evidence shows microorganisms thrived not long after the planet cooled. But how did non-living chemistry cross the threshold into life? One idea suggests simple molecules self-organized into chains capable of storing information, perhaps RNA before DNA. Another proposes life emerged from energy-rich hydrothermal vents on the ocean floor. Still others suggest life's building blocks arrived from space on comets or meteorites that bombarded the young Earth. Each idea has support. None are proven. Scientists have created amino acids in laboratory conditions. But producing a fully living system remains beyond reach. The origin of life may have been a unique event, or it may be a natural outcome whenever the right conditions exist. Until we find clearer evidence, the moment when chemistry first awakened into biology remains one of science's deepest mysteries. We do not know whether life began in the ocean or on land. The ocean seems an obvious cradle for early life. Hydrothermal vents on the sea floor provide rich chemistry and constant energy. But some researchers argue that shallow pools on land, subject to cycles of drying and refilling, could have concentrated molecules and driven essential reactions. Ultraviolet light from the sun could have powered key steps. Both environments seem plausible. Each offers strengths and faces challenges. The ocean dilutes molecules, making interactions difficult. Land-based pools may have been too unstable. Until stronger evidence emerges, we do not know whether life first stirred in the deep seas or in warm little ponds. The answer remains hidden in the deep past. We do not know why DNA has its specific structure. All life on Earth uses DNA to store genetic information. Its double helix is elegant and universal. But why this molecule and why this shape? Chemistry allows many possible ways to store information. RNA may have come first, but somewhere in life's early history, DNA took over. Its stability, reliability, and capacity for immense information made it uniquely suited. Yet we do not understand why its specific structure, a double helix with precisely paired bases, became the universal solution. Was it inevitable, dictated by chemistry? Or an accident, one successful outcome among many failed alternatives? The universality of DNA suggests it may be the best answer nature could find. Still, why life chose this exact path remains an open question. The origins of viruses are still unclear. Viruses are strange entities. They cannot reproduce on their own, relying instead on hijacking living cells. Yet they are not merely inert molecules. They evolve, adapt, and influence life on Earth. Where did they come from? Some scientists think viruses are relics from before fully living cells evolved. Others believe they began as genetic material that escaped from cells. A third possibility is that they were once living organisms stripped down to their simplest form. The truth may be that viruses arose in multiple ways. They blur the line between life and non-life. Their origins remain one of biology's most enduring mysteries. We do not know why some molecules became alive, while countless others did not. The early Earth was a chemical playground. Simple molecules formed everywhere. Among them, some began to link into more complex chains. But only a tiny fraction crossed the line into life. Why those molecules and not others? What special property allowed some to organize into self-replicating systems? Was life inevitable once the right ingredients came together? Or was it a rare accident? The leap from chemistry to biology is vast. We do not yet know how it happened. This uncertainty raises profound questions. If life is inevitable, the universe may be filled with living worlds. If it was a fluke, we may be utterly alone. We still do not know if life exists anywhere else in the universe. Earth is the only place where life is confirmed. But with billions of stars in our galaxy and billions of galaxies beyond, it seems unlikely we are alone. We have discovered thousands of exoplanets, many in habitable zones. Organic molecules are common in space. Mars shows signs of a wetter past. Moons like Europa and Enceladus hide oceans beneath ice. Conditions for life seem abundant. Yet the silence persists. We have not detected signals. We have not found microbes on Mars. We have not uncovered alien fossils. It is possible life is common but hard to detect, or exceedingly rare. Until we find even the simplest alien microbe, the question remains unanswered. We do not know if life could form from completely different chemistry. All life on Earth is built on carbon, water, DNA, and proteins. But must it be so? Some scientists think silicon could serve as the backbone of alien life. Others imagine organisms using ammonia instead of water, or exotic biochemistries in methane seas. We do not know if carbon and water are the only solution, or if the universe holds living systems stranger than we can imagine. If we discover alien life, it may look nothing like us. It could challenge our very definition of what it means to be alive. Consciousness arises from the brain, but we do not know how. Every thought, every memory, every flicker of awareness seems to arise from the brain. Scientists can measure electrical signals, track neural activity, even switch consciousness off with anesthesia. Yet none of this explains why there is an inner experience at all. Why should firing neurons create the feeling of being alive? A brain scan shows activity in the visual cortex when you see a sunset, but it does not explain why you experience the warmth of red and gold. Researchers have theories. Perhaps consciousness emerges when information integrates across the brain. Perhaps it requires specific neural patterns. Some even suggest awareness is a fundamental property of the universe itself. None of these truly explain the leap from matter to mind. Consciousness is the most ordinary thing. You experience it right now. Yet when we try to explain it, it slips through our fingers. Dreams fill our nights, but their purpose is still unknown. Every night, your mind conjures worlds. Some vivid and familiar, others strange and fragmented. These are dreams. No one truly knows why they happen. Some scientists think dreams help the brain process memories and emotions. Others believe they are random firings patched into stories. Still others suggest dreams prepare us for challenges, rehearsing scenarios safely. What makes dreams puzzling is their power. A nightmare can wake you in terror. A good dream can leave you smiling all day. Sometimes dreams even solve problems. We know the brain is active during dreaming, especially during rapid eye movement sleep. But the purpose behind it remains elusive. Dreams are familiar nightly journeys, yet their true meaning is still hidden. Our sense of time can speed up or slow down, and no one knows why. Think of a moment when time seemed to crawl. A near accident. A sudden fright. Now think of the opposite. Hours that vanished when you were absorbed in something you loved. Clock time is steady, but our experience of time is anything but. Some believe the brain has an internal clock that emotions alter. Fear may speed it up while calm slows it down. Others suggest we judge time by how many events we process. Childhood summers seemed endless because everything was new. Adult years slip past because routine compresses perception. But these are only theories. Time in the mind is elastic. It stretches, contracts, and sometimes seems to stand still. Why our experience of seconds and minutes flows so differently remains mysterious. We do not understand how memories are stored and recalled. Your entire life, every moment and memory, is stored somewhere inside your brain. Yet how those memories are kept and retrieved remains unclear. Memories are not like files in a cabinet. They are patterns of activity across neurons in different regions. The hippocampus helps weave these patterns. But exactly how the brain encodes a memory and later pulls it back is not fully understood. Sometimes memories change when recalled, reshaped before being stored again. Sometimes we create false memories that feel completely real. Why do some memories last a lifetime while others fade in days? Why does a certain scent unlock vivid scenes from childhood? Memory is the glue that makes us who we are. Yet the machinery behind it is still unknown. Emotions run deep, but their origins remain mysterious. Emotions shape every part of life. Joy pushes us forward. Fear holds us back. Anger flares. Sadness weighs heavy. But where do they come from? Scientists know emotions involve both body and brain. Your heart races when afraid. Tears well up when sad. But the origins are debated. Are emotions hardwired survival tools? Or are they constructed by the brain, shaped by culture and interpretation? Certain brain regions play roles. The amygdala processes fear. The prefrontal cortex regulates responses. But no single emotion center exists. Music can bring goosebumps. Scents trigger nostalgia. Sometimes we do not even know why we feel the way we do. Emotions are powerful guides, steering choices more than reason does. Yet how they arise remains one of the most intimate mysteries of being human. Creativity appears in sudden sparks, but we do not know where it comes from. An artist stares at a blank canvas, a writer at an empty page. Hours may pass with nothing. Then suddenly an idea arrives, clear, surprising, alive. Where did it come from? Creativity feels like a spark, but its origin is hidden. Some say it is the brain mixing old ideas in new ways. Others think it requires stepping away, letting the subconscious work while the conscious mind rests. Brain scans show different networks involved, some generating ideas, others judging them. But this does not explain the moment of inspiration. Why does the solution arrive suddenly? Why do some people overflow with creative ideas while others struggle? Creativity is one of humanity's greatest gifts. Yet the place where ideas come from remains a mystery. Déjà vu makes the present feel repeated, and no one knows why. You step into a room you have never been in, and suddenly everything feels strangely familiar. You know what will happen next, though you do not. This is déjà vu. It remains one of the strangest mysteries of the mind. Perhaps the brain misfires, creating a false signal of familiarity. Perhaps one part processes an experience slightly before another, making the moment feel like a repeat. What makes déjà vu so mysterious is its intensity. For a few seconds, reality feels doubled, both new and remembered. Almost everyone experiences it. Yet no one can predict when or why. Déjà vu reminds us that memory and perception are fragile. Placebos can heal, but the power behind them is still a mystery. Imagine taking a pill, being told it will ease your pain, and actually feeling better, even though the pill contained nothing at all. This is the placebo effect. And it is real. Doctors have seen placebos reduce pain, ease depression, even calm symptoms of Parkinson's disease. The effect seems to come from expectation. Belief triggers real changes in the brain and body. What makes the placebo strange is that it can work even when people know they are taking one. Somehow, the ritual of treatment taps into hidden healing pathways. But why some people respond strongly while others do not remains unknown. The placebo effect blurs the line between mind and body, showing us that belief itself can heal in ways we still do not understand. We do not know why we need sleep at all. Every night we surrender to sleep. We close our eyes, drift into dreams, and lose awareness for hours. But why? Sleep is dangerous. In the wild, a sleeping animal is vulnerable. Yet every species does it. Some scientists believe sleep helps the brain store memories. Others think it clears away waste. Sleep may restore energy, regulate emotions, and strengthen the immune system. No single explanation fits all evidence. Different animals sleep differently. Dolphins sleep with half their brain at a time. Some birds sleep while flying. What we know is that without sleep, minds and bodies quickly break down. Why we spend a third of our lives doing it remains a mystery. We do not understand why aging happens the way it does. Every living thing ages. Skin wrinkles, hair grays, muscles weaken. But why? One explanation points to DNA. Each time cells divide, protective caps called telomeres grow shorter. Eventually, cells stop dividing. Another theory blames accumulated damage from oxygen and other molecules. Yet nature presents exceptions. Some turtles show almost no signs of aging. Certain jellyfish appear able to revert to earlier life stages. Naked mole rats live far longer than expected. Why do some creatures resist aging while humans succumb? The answers remain elusive. Unlocking this mystery could transform medicine. But for now, aging is a riddle written into our very cells. The limits of human lifespan remain uncertain. The longest confirmed human life ended at 122 years. But was this the ceiling of human biology or a remarkable outlier? Some researchers argue humans have a hard limit. Beyond a certain age, the body cannot repair itself quickly enough. Others insist there is no strict maximum, only rising odds of frailty. Average life expectancy has climbed thanks to medicine, but maximum lifespan has barely budged. Almost no one lives past 115. Could humans someday reach 150 years? Or 200? The upper boundary remains hidden, waiting for discovery. Some animals can regenerate entire limbs, and we cannot explain how. If a salamander loses a leg, it grows a new one. If a starfish loses an arm, it rebuilds it. Some worms can regenerate an entire body from a single fragment. Humans cannot do this, except in the tiniest ways. When salamanders are injured, cells near the wound seem to reset, becoming flexible like embryonic cells. From there, they grow into muscles, bones, and nerves. Humans share many of the same genes. Yet our bodies do not use them the same way. If we could unlock this ability, damaged hearts could heal. Spinal cords could regrow. Limbs could return. But the full blueprint remains hidden. Why nature granted this power to some creatures while denying it to us is a mystery. Some creatures live far longer than expected, and we do not know why. Most animals follow a pattern. Small bodies live short lives. Large ones live longer. But exceptions exist. The Greenland shark swims for over 400 years. Bowhead whales live more than 2 centuries. Naked mole rats live 10 times longer than similar rodents. Scientists have found clues. Unusual proteins. Efficient DNA repair. Slow metabolisms. But no single answer explains them all. Each species seems to have its own key to longevity. These creatures remind us that aging is not fixed law, but a puzzle with many solutions. Some animals survive being frozen solid, and we do not understand how. The wood frog of North America freezes solid in winter. Its heart stops. Its body stiffens. Yet when spring warmth returns, it thaws and hops away unharmed. Certain insects and fish can do the same. Tardigrades can survive the vacuum of space. Some creatures use antifreeze molecules to prevent ice from shredding cells. Others use sugars that stabilize tissues. But exactly how their brains and hearts survive months without activity remains unclear. If we could master this trick, it might revolutionize medicine and space travel. For now, the secret belongs only to these hardy survivors. Whales live for centuries without much cancer, and no one knows how. The bowhead whale lives over 200 years. Despite its massive size and billions of cells, cancer is remarkably rare. This is Peto's paradox. Larger animals with more cells should have higher cancer rates. Yet whales and elephants do not. Elephants have extra copies of tumor suppressor genes. In whales, the explanation is murkier. Perhaps their DNA repair is unusually strong. Perhaps their metabolism slows damage. If we could unlock this mystery, it might revolutionize cancer treatment. Whales have cracked part of the code. Their secret drifts beneath the waves, unsolved. Birds can sense Earth's magnetic field, but the mechanism is still unclear. Every year, birds migrate across continents with uncanny accuracy. They travel thousands of miles and arrive at the same locations year after year. Part of their secret lies in sensing magnetic fields. But how? Some evidence points to tiny crystals of magnetite in their bodies. Other research suggests proteins in their eyes let them see magnetic fields as faint patterns. No single theory explains it all. Even on cloudy days, when the sun is hidden, birds stay on course. For birds, the world carries invisible directions. A compass we still do not understand. Monarch butterflies navigate continents with a map we cannot read. Every autumn, fragile monarch butterflies fly thousands of miles from North America to mountain forests in Mexico. No single butterfly completes the round trip. Those that return are several generations removed. Yet they arrive at the same groves year after year. Monarchs use the sun as a compass. They may also sense magnetic fields. But how they pass this knowledge between generations remains unknown. It is one of the most breathtaking migrations on Earth, guided by a hidden map no human has ever read. Migrating animals cross thousands of miles, and we do not know how they guide themselves. Salmon return to the exact stream where they hatched. Sea turtles crawl onto the same beach where they were born. Birds find the same trees each year. Scientists have found clues. Some animals use stars, the sun, or magnetic fields. But none of these fully explains their precision. How does a turtle cross an entire ocean to one patch of sand? Migration is one of life's oldest rhythms, a grand, mysterious dance written into instinct. Homing pigeons return home from anywhere, and the mystery persists. Release a homing pigeon hundreds of miles from home, and it will fly straight back. No map, no guide, just a hidden sense of direction. Some believe pigeons use the sun as a compass. Others suggest they detect magnetic fields or follow scent maps. But no explanation accounts for their uncanny accuracy. Pigeons find home from strange places under cloudy skies. Their secret compass remains uncovered. We do not know how humans first developed language. Language is what makes us human. With it, we share ideas, pass down stories, and build civilizations. But how did it begin? Our closest relatives communicate with gestures and sounds, but nothing approaches human speech. At some point, our ancestors made the leap from simple calls to structured language. Some theories suggest language began as hand signals. Others propose rhythmic sounds gradually became words. Language allows us to describe what is not present, to plan, to dream. Yet the first spark, the moment when humans first spoke, is lost in time. Laughter is universal, but its roots remain a puzzle. Wherever you go, people laugh. The sound crosses cultures and ages. Babies laugh before they speak. Why do we laugh? Some believe laughter began as a signal of safety. Early humans may have laughed to show threats had passed. Others trace it to primates at play, whose panting during rough games resembles laughter's rhythm. But laughter is more than survival. It lowers stress and bonds groups. We laugh not only at jokes but also at relief, awkwardness, even sorrow. Why should a sound carry such power? Laughter is ancient and mysterious. Its roots remain hidden. Music moves us deeply, but science cannot explain why. A melody can make us cry. A rhythm can make our hearts race. A song can bind us to forgotten memories. Music has no obvious survival function, yet it shapes human life across every culture. Some suggest music evolved as social glue. Others think it began as courtship. Still, others argue it is a beautiful accident of evolution. Music can synchronize heartbeats. It calms newborns. It stirs armies to march. Why should organized sound reach so deeply into our minds? Science has no clear answer. Music remains one of the most universal, mysterious forces in human life. Love is powerful and complex, but its full nature is still unknown. Love shapes lives more than almost anything else. It binds parents to children, partners to one another, friends across time. Yet science cannot fully explain it. Biology shows pieces. Love floods the brain with dopamine and oxytocin. Evolution suggests it keeps parents together long enough to raise offspring. But these explanations do not capture the full experience. Why does love sometimes arrive suddenly? Why does it last lifetimes in some cases and fade in others? Love is both universal and unique. Its full nature remains one of the most profound mysteries of being alive. Humans cry tears of emotion, and no one knows why. Tears protect eyes. But only humans shed tears for emotional reasons, when sad, joyful, frustrated, or overwhelmed with laughter. One idea suggests tears are social signals, showing vulnerability. Another proposes they release stress chemicals. What deepens the mystery is that we cry for opposite feelings. Tears come with grief and with joy. Tears make the invisible visible. But why humans alone evolved this response remains unsolved. Myths appear across cultures in similar forms for reasons we do not understand. From deserts to islands, cultures separated by oceans tell stories that echo one another. Myths of great floods, sky gods, tricksters, and underworlds appear again and again. The Sumerians spoke of a great deluge. So did the Hebrews, the Greeks, the Chinese, and peoples of the Pacific Islands. How did the same story reach such distant shores? Some suggest human minds are wired for story, and certain themes arise from shared experience. Floods are memorable. They leave survivors with tales to tell. Others believe myths spread through migration and trade, carried across continents before written history began. Still others wonder if myths are shaped by deeper patterns in the brain. Perhaps certain archetypes arise inevitably from the way minds work. The strange recurrence of similar stories across the globe remains a mystery. These echoes suggest something profound about human nature, something we have not yet understood. We do not know why we dream of falling, flying, and being chased. Dream themes repeat across cultures and centuries. People dream of teeth falling out, of being unprepared for exams, of running but unable to move. Why do these images recur? Are they hardwired into the human brain? Some researchers think common dreams reflect universal anxieties. Others suggest they arise from how the sleeping brain processes movement and memory. Yet no one has proven why the same strange scenarios appear in the minds of people separated by continents and millennia. Dreams may hold clues to how the mind works. their recurring patterns remain unexplained. We often cooperate with strangers, and the origins of this instinct are unclear. Humans help not only family, but also strangers. We donate blood, we volunteer, we risk ourselves for people we may never meet. This behavior defies simple evolutionary logic. Helping relatives makes genetic sense. Helping those who can help you back makes strategic sense. But humans often go beyond both. We sacrifice without hope of reward. We give to charities on distant continents. We leap to rescue strangers from danger. Some researchers think group selection shaped this instinct. Tribes that cooperated outcompeted those that did not. Others argue reputation and social bonding explain it all. But these explanations feel incomplete. Something in us seems drawn toward cooperation, toward kindness, in ways that exceed calculation. The willingness to help strangers is one of humanity's most beautiful and mysterious traits. Its origins remain unclear. We do not know why humans are so drawn to ritual and ceremony. Every culture creates rituals. Weddings, funerals, coming-of-age ceremonies, religious rites, seasonal celebrations. Why do humans need these formal, repeated actions? Some scientists think rituals reduce anxiety by creating predictability. Others suggest they strengthen group identity and social bonds. Yet rituals often seem to exceed their practical function. They carry meaning that resists explanation. Why should standing in a particular place, wearing particular clothes, speaking particular words, feel so important? Ritual may be older than language. It may touch something deep in the human psyche that we do not fully understand. Civilizations rise and fall, but the deep forces behind them remain debated. Mighty civilizations have grown, flourished, and collapsed. The Maya, Rome, Mesopotamia all rose to greatness only to fall. Some point to climate change or war. Others see internal patterns of growth and decay. Economic inequality, political corruption, resource depletion, and disease have all been blamed. Historians have proposed cycles. Empires grow strong, overextend, and weaken. New powers rise from the margins. The pattern seems to repeat. What is striking is how sudden collapse can be. Great cities abandoned, knowledge lost, writing systems forgotten for centuries. The Maya left pyramids in the jungle. The Minoans vanished from history. Rome, which seemed eternal, crumbled in decades. Could the same happen to us? Some scientists see echoes of past collapses in modern stresses. Civilization is fragile. The forces that make it thrive or fail are not fully understood. The mystery of rise and fall haunts the present as much as the past. We do not understand why some societies become creative while others do not. Some periods burst with innovation. Athens in the 5th century BCE, Florence during the Renaissance, Silicon Valley in recent decades. What creates these explosions of creativity? Some point to freedom and trade. Others emphasize education, patronage, or the mixing of cultures. Perhaps it is random, a lucky coincidence of talented people in the right place. Yet creativity often clusters in ways that resist simple explanation. Why did the scientific revolution happen in Europe and not elsewhere? Why did jazz emerge in New Orleans? The spark that ignites cultural creativity remains one of history's deepest mysteries. Human curiosity drives us, but its source is still unknown. Why do we wonder? Why do we look at the stars and ask questions no other creature asks? Curiosity is one of humanity's defining traits. Children ask why endlessly. Scientists dedicate lives to questions. Explorers risk everything for discovery. But where does this drive come from? Some say curiosity extends survival instincts. Knowing more about the world helps us survive. Others believe it evolved as an advantage for exploration and invention. But curiosity often goes beyond survival. It drives us to study galaxies billions of years away, to decode ancient languages, to ask questions with no practical answer. Why should we care about the origin of the universe? It will not help us find food or shelter. Yet we cannot stop asking. Curiosity may be what makes us human. But its ultimate source, the spark behind the question why, remains a mystery we cannot solve. We do not understand why humans alone developed advanced technology. Other animals use tools. Crows fashion hooks. Chimpanzees crack nuts with stones. Elephants use branches to swat flies. But only humans have built cities, written books, and flown to the moon. Why did we alone take this path? Our brains are larger, relative to body size. We have opposable thumbs. We developed language. Each explanation has merit, but none fully explains the gap. Other species are intelligent. Some are social. Some communicate in complex ways. Yet none invented writing or calculus. The leap from stone tools to smartphones happened in an evolutionary eye blink. What made humans capable of this acceleration remains unclear. Storytelling is universal, but no one knows why we need it. Every culture tells stories. They carry heroes and villains, struggles and triumphs. Around campfires and in city squares, on cave walls and in digital streams, humans have always told tales. Some suggest stories pass on knowledge. A story about danger teaches without risk. A story about success shows the path. Others think they bind communities, creating shared histories and values. But stories often go beyond these roles. They create worlds that never existed. They fill us with emotions for people who are not real. We weep for fictional characters. We cheer for heroes who never lived. No other species does this. Why do humans need stories? Perhaps stories are how we make sense of chaos. Perhaps they are how we rehearse life without living it. Perhaps they are how we feel less alone in a vast and indifferent universe. Storytelling is as ancient as language. Its true purpose remains hidden, but the hunger for narrative burns as strongly as ever. We do not understand why music gives us chills. Some moments in music raise goosebumps. A singer hits a soaring note. A chord resolves after tension. A melody swells unexpectedly. This physical response, called frisson, remains mysterious. Why should sound waves trigger shivers down the spine? What evolutionary purpose could this serve? Some researchers think frisson occurs when music violates and then fulfills expectations. Others link it to dopamine release in the brain. But these explanations feel incomplete. Music reaches places words cannot. Its power to move the body remains one of the deepest mysteries of the human experience. Ball lightning appears as glowing spheres, and we do not know what causes it. Most people know lightning as a flash, a jagged streak splitting the sky. It lasts a fraction of a second. But there is a stranger phenomenon that defies this pattern. Ball lightning appears as a glowing sphere of light, drifting silently through the air, sometimes lasting several seconds before vanishing or exploding. For centuries it was dismissed as myth, a trick of the eyes or folklore. But credible sightings and recordings now confirm it is real. Witnesses describe orbs ranging from golf ball to beach ball size. They glow white, yellow, or blue. They hover, drift through walls, and sometimes pass through aircraft. Some theories describe plasma trapped by electromagnetic fields, sustained temporarily by unknown forces. Others imagine vaporized silicon glowing after a lightning strike hits soil. But no explanation fits every account. Laboratory attempts to create ball lightning have succeeded only briefly. Ball lightning remains one of nature's strangest atmospheric mysteries. It appears without warning and vanishes without explanation. Sprites and jets flicker above thunderstorms, and we have only recently discovered them. High above powerful thunderstorms, brief flashes of color illuminate the upper atmosphere. Red sprites, blue jets, and elves are among the names given to these transient luminous events. They were only photographed for the first time in the 1990s. Pilots had reported strange lights above storms for decades. Scientists were skeptical. Now high-speed cameras confirm these phenomena are real. They occur so briefly that the human eye barely registers them. Yet they extend for miles, towering above the clouds. What triggers them? How common are they? Do they affect the atmosphere in ways we have not measured? Our understanding of lightning has expanded upward into realms we barely knew existed. Earthquake lights appear in the sky during some earthquakes, and no one knows what causes them. During powerful earthquakes, witnesses report glowing lights in the sky, flickering flames, flashes like lightning, strange orbs floating over fault lines. These earthquake lights have been reported throughout history. Ancient chronicles describe them. Modern cameras have captured them. One theory suggests that stressing rocks releases electrical charges that rise through the ground and ionize the air. Another proposes that gases near the surface glow when disturbed. Yet another suggests piezoelectric effects in quartz-rich rocks. Not every earthquake produces lights. When they appear, they sometimes precede the quake itself, suggesting they could potentially serve as warnings. Scientists have struggled to reproduce these lights in laboratories. The conditions that create them remain elusive. Earthquake lights are among the most eerie natural mysteries. They flicker at the intersection of geology and atmospheric physics, defying easy explanation. Some volcanic eruptions are catastrophic, and the exact triggers remain mysterious. Most eruptions are manageable. But every so often, a volcano erupts with unimaginable fury, altering climate and spreading devastation. Scientists know pressure builds as magma rises, but the exact tipping point remains uncertain. Events like Krakatoa and Mount Toba unleashed energy rivaling nuclear weapons. Toba may have nearly wiped out humanity. Modern science still cannot predict which volcanoes will erupt catastrophically or when. Volcanoes remind us that Earth is alive, capable of mysteries we have yet to master. We do not know why plate tectonics began on Earth. The surface of our planet is alive with motion. Continents drift, mountains rise, oceans open and close. Without plate tectonics, Earth would not have its landscapes. Life itself may depend on this churning. But why did it begin here, and not on other planets? Mars and Venus have no active tectonics. Did water act as lubricant? Did internal heat reach the right balance? Why Earth alone developed this feature remains unsolved. The origin of Earth's water is still uncertain. Water covers most of Earth. It is essential to life. Yet its origin remains mysterious. Did water arrive on asteroids and comets? Some evidence supports this, but chemical fingerprints do not always match. Another idea suggests water was present from the beginning, trapped in Earth's mantle. Perhaps both are true. The balance is still debated. The far side of the Moon looks strangely different, and we do not know why. The near side of the Moon is covered with dark maria, vast plains of cooled lava. The far side is rugged and mountainous, with almost no maria. Why should the two faces be so different? One idea suggests uneven heating from Earth. Another proposes ancient collisions. The Moon should be symmetrical, yet it is not. Even as landers touch its surface, the far side keeps its mystery. Earth's magnetic field powers from the core, but details remain unclear. Deep beneath us lies Earth's core, molten iron churning to generate our magnetic field. This field shields us from solar radiation. Without it, our atmosphere might be stripped away like Mars. But we do not fully understand how it works. We cannot drill to the core. We rely on indirect clues. Why Earth kept its field while Mars lost its remains uncertain. Earth's magnetic poles sometimes flip, and the cause is unknown. Every so often, Earth's magnetic poles switch places. North becomes south. The last full reversal happened about 780,000 years ago. Scientists believe turbulence in the outer core causes these flips, but the exact trigger is unclear. During reversals, the field weakens, exposing Earth to more radiation. Did past reversals influence evolution? We do not know. Ice ages come and go, and we still do not know what drives them. For millions of years, Earth's climate has swung between ice ages and warmer periods. Some explanations point to changes in Earth's orbit. Others suggest volcanic eruptions or carbon feedback loops. The rhythm of ice and thaw shaped human history, but the underlying engine remains unclear. Mass extinctions strike suddenly, and their causes remain unsettled. 5 times in Earth's history, life has nearly been wiped out. Asteroid impacts, supervolcanoes, climate shifts have all been proposed. Sometimes evidence points clearly. Other times it is murky. Why some species vanish while others survive is equally mysterious. Mass extinctions remind us of life's fragility, but also its resilience. Saturn's rings appear young, and we do not know how they formed. Saturn's rings are breathtaking. Vast bands of shimmering ice and dust. Yet they may be only a few 100 million years old. If ancient, they should be darker, dirtied by impacts. They are strangely clean. Perhaps a moon wandered too close and was torn apart. Perhaps comets shattered. No explanation is certain. Saturn's rings may be temporary. We live in a brief era when Saturn wears this crown. Uranus spins on its side, and no one knows why. Among the planets, Uranus is strange. It rotates almost horizontally, tilted by 98 degrees. A colossal ancient impact may have knocked it over. But such a collision should have left signs. Whatever the cause, Uranus remains unique. Venus rotates backward, and its strange past is still debated. Most planets spin in the same direction they orbit. Venus rotates the other way. On Venus, the Sun rises in the west. A massive collision may have flipped it, or tidal interactions gradually reversed its spin. No theory fully explains Venus. Neptune is full of storms we do not fully understand. At the edge of the solar system, Neptune howls with winds faster than any on Earth. The Great Dark Spot was discovered in 1989. It vanished within years. Other storms have since appeared and faded. Why does Neptune, so far from the Sun, have such violent weather? Neptune remains a distant storm world, its mysterious weather showing us that even in frozen reaches, chaos can reign. Jupiter's Great Red Spot has raged for centuries, and its future is uncertain. The Great Red Spot has swirled for at least 350 years. A storm so large it could swallow Earth. Yet it is shrinking. Once 3 Earths could fit across it. Now barely 1. Why did the storm form? Why has it lasted so long? Will it vanish? The Great Red Spot is a cosmic paradox. Ancient and fragile. Comets cluster in a distant cloud we have never seen directly. Comets swoop in from the edges of the solar system. Astronomers believe they come from the Oort cloud, a vast reservoir of icy bodies beyond Pluto. The Oort cloud may contain trillions of objects. Yet it has never been observed directly. The objects are too small and distant. We know it only from the comets it sends us. Many moons hide oceans beneath ice, but we do not know what lives there. Moons like Europa and Enceladus hide oceans beneath shells of ice. Some may be larger than all Earth's seas combined. On Earth, where water exists, life follows. Could ecosystems exist beneath alien ice? We have hints. Enceladus sprays water rich with organic molecules. But we cannot yet see into these oceans. What strange life might swim there remains locked beneath ice, waiting in the dark. Titan has seas of methane, and something keeps replenishing them. Titan has lakes and rivers, but they are made of liquid methane. Methane should be destroyed by sunlight over time. Yet Titan's seas remain. Something keeps replenishing them. Cryovolcanoes may release methane from below. Titan's methane cycle mirrors Earth's water cycle in eerie ways. The source that keeps its seas full remains a mystery. Mars once had flowing rivers, but we do not know where the water went. Billions of years ago, Mars was different. Vast river valleys carved the surface. The planet may have had oceans. Today it is dry and frozen. Some water may be locked as ice underground. Some may have escaped into space when Mars lost its magnetic field. The full story is unclear. Mathematics describes the universe with uncanny accuracy, but we do not know why. Mathematics is a language of patterns. Yet equations dreamed up on paper turn out to govern stars and atoms. Einstein's equations predicted black holes before anyone saw one. Maxwell's formulas described radio waves before detection. Why should abstract symbols map so exactly onto reality? Some argue math is discovered, revealing truths built into the cosmos. Others say math is shaped by human minds. Neither explains the eerie accuracy. The constants of nature seem fixed, yet their values remain unexplained. The speed of light, the strength of gravity, these numbers define how the universe works. But why do they have these values? No theory explains why gravity, electromagnetism, or nuclear forces take the strengths they do. Some suggest countless universes exist with different values, and we live in one where life is possible. The constants are like settings on a cosmic dial, fixed, precise, and unexplained. We do not know if true randomness exists. Flip a coin, roll dice, randomness seems obvious. But at the quantum level, particles behave unpredictably. Is this true randomness or complexity beyond understanding? Einstein believed hidden laws must govern quantum events. Experiments suggest otherwise. If true randomness exists, uncertainty is part of reality itself. Time itself remains one of science's greatest mysteries. We live in time. We feel it flow. Yet science cannot fully explain what time is. Einstein showed time is not absolute. It bends with speed and gravity. But why do we experience it as a one-way arrow? Why does the past feel fixed while the future remains open? Time governs every heartbeat. Its true nature remains profound mystery. Matter exists, but antimatter nearly vanished, and we do not know why. The Big Bang should have created equal amounts. But matter won. If balanced, everything would have annihilated, leaving only light. Something broke the symmetry. Some process favored matter. We do not fully understand. You exist because symmetry was broken. Particles have mass. but we do not fully understand what gives it to them. The Higgs boson confirmed that an invisible field gives particles mass. But why does the Higgs field exist? Why does it have the strength it does? The Higgs opened a door. Behind it lies deeper mystery. Reality may be continuous or pixelated, and no one knows which. To our eyes, reality feels smooth. But at the smallest scales, space may be grainy like pixels. The Planck scale is far beyond observation. Whether the universe is continuous or digital remains a strange question. There may be a smallest possible length, but we have not found it. Physics pushes us to smaller scales. At some point, there may be a limit beyond which smaller has no meaning. This is thought to be the Planck length, but no experiment can reach it. If space has a smallest unit, reality has a bottom floor. The laws of physics could have been different, but no one knows why they are what they are. The universe runs on elegant laws, but they could have been otherwise. Some imagine universes with different laws. We exist in one where conditions allow life. Others seek deeper principles. None have been found. Whether we will ever truly understand any of this remains perhaps the greatest mystery of all. Science has carried us far. We have mapped galaxies. We have split atoms. We have decoded DNA. Yet each answer reveals more questions. Perhaps one day we will explain consciousness, the origin of life, the nature of time. Or perhaps there will always be questions beyond reach. The greatest mystery may not be the universe itself, but whether human minds can ever truly comprehend the totality of reality. As you drift towards sleep, hold that thought gently. Curiosity itself is part of the mystery. To wonder is to be human. To seek is to be alive. The questions may never end, but neither will our search. Let us now return to some of these mysteries and explore them a little deeper. There is no rush. The night is long, and wonder is patient. The mystery of existence has puzzled philosophers and scientists for millennia. Why is there anything at all? This question appears simple, yet it resists every attempt at explanation. Consider what it would mean for there to be nothing. No space, no time, no matter, no laws, no possibility. Absolute non-existence. But can we even conceive of such a state? Our minds evolve to understand things, not their absence. Perhaps the concept of nothing is itself incoherent. Some philosophers argue that existence is necessary, that there must always be something, because pure nothingness is unstable or impossible. If this is true, then asking why there is something misses the point. There could never have been nothing. Others suggest the question has no answer, that existence is a brute fact, requiring no explanation. Still, the question haunts us. It is the deepest puzzle of all, and perhaps that is fitting. The foundation of everything should be mysterious. When you look at the stars, you are looking at something that did not have to exist. And yet it does. And so do you. That simple fact is enough to inspire wonder for a lifetime. The fine structure constant determines the nature of light and matter. There is a number in physics that appears everywhere. It governs how light interacts with atoms. It determines the size of atoms themselves. It sets the strength of the electromagnetic force. This number is called the fine structure constant. Its value is approximately 1 divided by 137. But why this value? If the constant were slightly different, atoms would behave differently. Chemistry would change. Life as we know it might be impossible. Physicists have measured this number with incredible precision, but no one knows why it takes the value it does. Is it random? Is it fixed by deeper principles we have not discovered? Is it different in other universes? The fine structure constant is a reminder that beneath the familiar world lies a layer of numbers we cannot explain. The universe runs on mathematics, and the equations have constants that remain mysterious. The proton does not decay, and we do not know why. Every atom in your body contains protons. They have been stable since the earliest moments of the universe. But are they truly eternal? Some theories predict that protons should eventually decay, breaking apart into lighter particles over immense timescales. If protons decay, then all matter is temporary. Given enough time, everything would dissolve. Experiments have searched for proton decay for decades. Giant tanks of water buried deep underground wait for a single proton to break apart. So far, none have. The lower limit on proton lifetime is now estimated at more than 10 to the power of 34 years. That is longer than the current age of the universe by a factor of trillions of trillions. But this does not mean protons are stable forever. It only means we have not caught one decaying yet. The fate of matter itself may depend on whether protons are truly eternal. And we still do not know the answer. The strong nuclear force holds atomic nuclei together, but its precise behavior is complex. Inside every atom lies a nucleus containing protons and neutrons. Protons are positively charged and should repel each other. Yet nuclei hold together. The strong nuclear force is responsible. It is the most powerful force in nature, but it operates only at incredibly short distances. Despite decades of study, calculating the strong force from first principles remains enormously difficult. The equations are so complex that even supercomputers struggle. Why is the strong force so powerful, yet so short-ranged? Why does it have the properties it does? The force that holds matter together remains only partially understood. Its mysteries are hidden within every atom. We do not know why there are 3 generations of matter. Fundamental particles come in families. Electrons have heavier cousins called muons and tau particles. Quarks come in 6 varieties, arranged in 3 pairs. Why 3? Why not 2 or 4 or more? The Standard Model of Physics describes these particles beautifully, but it does not explain why nature chose 3 generations. Some theories predict additional generations. Experiments have searched and found none. The 3 we have seem to be all there are. But why? This pattern remains unexplained. The particle zoo follows rules we can describe but not justify. We do not know whether neutrinos are their own antiparticles. Neutrinos are ghostly particles that barely interact with matter. Trillions pass through your body every second without touching a single atom. One of the deepest questions about neutrinos is whether they are their own antiparticles. If so, they would be called Majorana particles, named after the physicist who proposed the idea. Experiments around the world search for evidence of this. The answer could reveal why matter dominates antimatter in the universe. But so far, the question remains open. Neutrinos keep their secrets well. The magnetic monopole has never been found. Magnets have two poles, north and south. Cut a magnet in half, and each piece has its own north and south. But could there be particles with only one magnetic pole? A north without a south? These hypothetical particles are called magnetic monopoles. Many theories predict they should exist. They would have formed in the early universe. They would revolutionize our understanding of electromagnetism. Yet, despite decades of searching, not one has been found. Either monopoles are extraordinarily rare, or our theories are wrong, or they simply do not exist. The absence of magnetic monopoles remains a puzzle at the heart of physics. We do not understand why certain constants have the values they do. The mass of the electron, the charge of the proton, the strength of gravity. These numbers appear fundamental. But are they truly constant? Could they change over time? Could they be different elsewhere in the universe? Some observations hint that constants might vary slightly over cosmic time. Others find no change at all. If constants are truly fixed, something must determine their values. If they can vary, our understanding of physics needs revision. Either way, the constants of nature remain mysterious. They define reality, yet we cannot explain them. Cosmic inflation solved problems but created new puzzles. In the first fraction of a second after the Big Bang, the universe may have expanded faster than light. This theory, called inflation, explains why the cosmos is so uniform and flat. But what drove inflation? What is the inflaton field that supposedly caused it? Why did inflation start, and why did it stop? Inflation is remarkably successful at explaining observations, but its underlying mechanism remains unknown. Some physicists wonder if inflation really happened. Others search for alternatives. The very success of inflation creates new questions. Solving one puzzle often reveals another hiding behind it. We do not know the exact value of the Hubble constant. The universe is expanding. The rate of that expansion is called the Hubble constant. Measuring it precisely should be straightforward. But different methods give different answers. Observations of the early universe, using the cosmic microwave background, give one value. Observations of nearby supernovae give another. The discrepancy is small but persistent. Is there an error in our measurements? Or is something wrong with our understanding of the universe? This tension in cosmology is called the Hubble tension. It may hint at new physics, or it may simply be a measurement problem. For now, we do not know. The expansion of the universe itself contains unsolved mysteries. We cannot explain why the cosmological constant is so small. Dark energy drives the accelerating expansion of the universe. Its value is described by the cosmological constant. When physicists calculate what this constant should be from quantum mechanics, they get an answer vastly larger than what we observe, off by a factor of 10 to the power of 120. This is sometimes called the worst prediction in the history of physics. Why is the cosmological constant so small? Why is it not zero? These questions touch the deepest foundations of physics. The smallness of dark energy remains one of the most profound mysteries we face. We do not know whether the universe will end. The cosmos had a beginning. Will it have an end? Current evidence suggests the universe will expand forever, but dark energy could change. New physics could intervene. Perhaps the universe will reach heat death, slowly fading into uniform emptiness. Perhaps it will experience a big rip, torn apart by accelerating expansion. Perhaps vacuum decay will transform reality itself. Or perhaps the cosmos will endure forever, in some form we cannot imagine. The ultimate fate of everything remains unknown. We can model scenarios, but we cannot be certain which will unfold. The ending of the cosmic story is still being written. We do not know how stars form in some environments. Stars form when clouds of gas collapse under gravity. This process is well understood in many contexts. But in some environments, star formation seems impossible. The gas should be too hot, or too sparse, or too turbulent. Yet stars appear anyway. How do stars form in the centers of galaxies, where conditions seem hostile? How did the first stars ignite in a universe with no metals? Each environment presents its own puzzles. Star formation is more complex than simple collapse. The birth of stars still holds surprises. We do not fully understand how galaxies form and evolve. Galaxies are vast collections of stars, gas, and dark matter. They come in many shapes and sizes. But how do they form? Computer simulations can reproduce many observed features, but discrepancies remain. Why do galaxies have the sizes they do? How do supermassive black holes influence galactic evolution? What role does feedback from star formation play? Each observation adds detail. Each simulation reveals new questions. Galaxies are the basic building blocks of the cosmic structure, yet their life cycles remain only partially understood. The nature of gamma-ray bursts took decades to unravel, and mysteries remain. Gamma-ray bursts are the most energetic events in the universe. In seconds, they release more energy than the Sun will produce in its entire lifetime. We now know that long bursts come from the collapse of massive stars. Short bursts come from merging neutron stars. But questions remain. What determines the burst's duration? Why do some stars produce bursts while others do not? Gamma-ray bursts are cosmic fireworks. Their violence is extreme, and their details are still being deciphered. The origin of ultra-high energy cosmic rays is still debated. Cosmic rays bombard Earth constantly. Most come from the Sun or from supernova remnants. But some arrive with enormous energies. The most extreme cosmic rays carry the energy of a baseball thrown at high speed, packed into a single particle. What could accelerate particles to such speeds? Active galactic nuclei? Colliding galaxy clusters? Unknown processes? We detect these particles hitting our atmosphere, but tracing them back to their sources is difficult. Magnetic fields bend their paths. The most energetic particles in the universe remain mysterious. Their origins are still unknown. We do not fully understand how cosmic magnetic fields formed. Magnetic fields permeate the universe. They thread through galaxies, fill galaxy clusters, and may even exist in the voids between. Where did these fields come from? Did they arise from primordial processes in the early universe? Or did they grow from tiny seeds amplified over time? Theories abound, but direct evidence of the origin remains elusive. Cosmic magnetism shapes the universe in subtle ways. Its beginnings are still being investigated. The reionization of the universe is not fully understood. After the cosmic microwave background was released, the universe entered a dark age. Neutral hydrogen absorbed light. Space was opaque. Then something changed. The first stars or galaxies began emitting ultraviolet light. This light ionized the hydrogen, clearing the fog. The universe became transparent again. This process is called reionization. We know it happened, but the details are unclear. Which sources provided the ionizing photons? When did reionization begin and end? Did it happen uniformly or in patches? The epoch of reionization is the cosmic dawn, and its specifics remain shrouded in uncertainty. We do not know if there are primordial black holes. Black holes form when massive stars die, but some might have formed in the early universe, before stars existed. These primordial black holes could have any mass. Some might be tiny. Others could be enormous. Could dark matter consist of primordial black holes? Could they seed the supermassive black holes we observe in galaxies? Searches continue. Some gravitational wave signals have hinted at black holes with unexpected masses. Could these be primordial? The question remains open. Primordial black holes are hypothetical. Their existence is neither proven nor ruled out. We do not understand why some neutron stars are so magnetic. Neutron stars are incredibly dense. Some have magnetic fields trillions of times stronger than Earth's. These magnetars produce violent flares of energy. But why do some neutron stars become magnetars while others do not? Is it the way the star collapsed? The rate of rotation? Some process we have not identified? Magnetars are among the most extreme objects in the universe. Their origins remain mysterious. We do not know if strange matter exists. Under extreme conditions, quarks might rearrange into strange matter, a hypothetical form containing strange quarks. Strange matter might be more stable than ordinary matter. If so, neutron stars could convert into strange stars. Some theories predict strange matter could be created in particle collisions. Others suggest it might not exist at all. The existence of strange matter remains unconfirmed. It is a possibility at the edges of physics. The interior structure of neutron stars is uncertain. Neutron stars contain matter crushed to incredible densities. But what exactly is inside? The outer layers are relatively well understood, but the core remains mysterious. Does it contain only neutrons? Or exotic particles like hyperons or free quarks? The equation of state, which describes how matter behaves at these densities, is not precisely known. Gravitational wave observations of neutron star mergers provide clues, but the interior remains hidden. The densest matter in the universe keeps its secrets. We do not fully understand magnetism at the quantum level. Magnetism arises from the motion and spin of electrons. At the quantum level, things become strange. In some materials, magnetic moments align in unexpected patterns. Frustrated magnets, where geometry prevents simple alignment, exhibit strange behavior. Quantum spin liquids, where magnetic order never forms even at absolute zero, challenge our understanding. Magnetism is familiar, but its quantum foundations still surprise us. We do not understand high-temperature superconductivity. Some materials conduct electricity without resistance when cooled to extreme temperatures. This is superconductivity. Most superconductors require temperatures near absolute zero, but some materials superconduct at higher temperatures. These high-temperature superconductors were discovered decades ago. Yet we still do not have a complete theory explaining them. Understanding high-temperature superconductivity could revolutionize technology, but the mechanism remains elusive. We do not know why water has so many anomalous properties. Water is essential for life. It is also deeply strange. Most liquids become denser as they cool. Water is densest at 4 degrees Celsius and becomes less dense as it approaches freezing. That is why ice floats. Water has unusually high surface tension, specific heat and boiling point. These properties are crucial for life and for climate. But why is water so anomalous? The hydrogen bonding between molecules explains some of it, but the full picture remains incomplete. The most familiar substance on Earth holds mysteries we have not fully solved. We do not understand how anesthesia works. Millions of surgeries depend on anesthesia to render patients unconscious. But the precise mechanism is not known. Anesthetics affect the brain in ways we can measure. But how exactly do they suppress consciousness? Different anesthetics have different chemical structures, yet they produce similar effects. This convergence is puzzling. We use anesthesia daily, yet consciousness and its suppression remain poorly understood. We do not know why humans yawn. Yawning is universal. Babies yawn. Animals yawn. Even fish yawn. But why? Theories suggest yawning cools the brain, or increases alertness or signals tiredness. None are fully proven. Yawning is contagious. Seeing someone yawn makes you want to yawn. Why should that be? Something so simple and common remains scientifically unexplained. We do not know why we itch. Itching seems straightforward, but the mechanisms are complex and poorly understood. Itch is distinct from pain. It has its own neural pathways. But why did it evolve? What purpose does chronic itch serve? Some conditions cause unbearable itching with no visible cause. We cannot always explain why. The sensation that makes you scratch remains partly mysterious. We do not fully understand the function of sleep stages. Sleep is divided into stages. Light sleep, deep sleep, and REM sleep cycle throughout the night. Each stage seems important, but their precise functions are debated. Deep sleep may restore the body. REM sleep may consolidate memories, but the details are unclear. We spend a third of our lives sleeping, yet the purpose of each phase remains partially unknown. We do not know why we forget. Memory is essential, but so is forgetting. Why do we lose memories? Is it decay over time? Interference from new memories? Active erasure by the brain? Each theory has evidence. None explains everything. Forgetting may be necessary for mental health and efficient thinking, but its mechanisms are not fully mapped. The gap between remembering and forgetting is one of the mind's deepest mysteries. We do not understand how birds know when to migrate. Every year, birds migrate at precise times. They seem to know when seasons are changing before the changes are obvious. How do they know? Day length plays a role, but internal biological clocks also matter. The interplay of light, hormones, and genetics remains complex. Different species use different cues. Migration timing is a feat of biological precision. Its full explanation is still incomplete. We do not understand how some animals detect earthquakes before they happen. Reports exist of animals behaving strangely before earthquakes. Dogs bark. Birds flee. Snakes emerge. Is this real? If so, what do animals sense? Some suggest they detect subtle vibrations or chemical changes. Others are skeptical that any reliable signal exists. The idea that animals can predict earthquakes is tantalizing, but scientific evidence is mixed. The mystery persists in the boundaries between observation and explanation. We do not know how the immune system knows when to stop attacking. The immune system defends against pathogens, but it must also recognize when to stop. Autoimmune diseases occur when the immune system attacks the body's own tissues. Why does this balance sometimes fail? The signals that regulate immune response are complex. We understand many of them, but the full picture is incomplete. The body's defense system is remarkably sophisticated. Its regulation remains only partially understood. We do not understand how cells decide their fate. A single fertilized egg becomes a complete organism with trillions of specialized cells. How does each cell know what to become? Genes are the same in every cell. Yet cells differentiate into muscle, bone, brain, and more. Epigenetics, signaling pathways, and transcription factors play roles, but the complete choreography of development is still being mapped. The unfolding of life from a single cell is one of biology's greatest mysteries. We do not fully understand how the brain stores long-term memories. Short-term memories become long-term through consolidation. But how exactly are memories stored for decades? Synaptic connections strengthen. Proteins are synthesized, but the precise encoding is not known. How can a memory of childhood persist through the constant turnover of molecules in the brain? The permanence of memory in a changing brain is a puzzle we have not solved. We do not know what dark matter particles are. We know dark matter exists because of its gravitational effects, but we have never detected a dark matter particle directly. Candidates include weakly interacting massive particles, axions, and sterile neutrinos. Experiments search for each. So far, all searches have come up empty. Either dark matter is even more elusive than expected, or it consists of something we have not imagined. The invisible substance that shapes galaxies remains unidentified. We do not know if the universe is deterministic or truly random. Does the future follow inevitably from the past? Or is there genuine chance in the cosmos? Quantum mechanics introduces probability, but does this reflect true randomness or simply our ignorance of deeper variables? The debate has continued for a century. Experiments support quantum randomness, but interpretations vary. Whether the universe is a clockwork or a dice game remains philosophically and scientifically open. We do not know if wormholes can exist. Einstein's equations permit wormholes, tunnels through space-time, connecting distant regions. But would they be stable? Could anything pass through? Would they even form naturally? Wormholes remain mathematical possibilities. No evidence suggests they exist in nature. The idea of shortcuts through space-time is tantalizing, but reality may not permit them. We do not know if time travel is possible. Einstein showed that time is flexible. It slows near massive objects. It stretches at high speeds. But can we travel backward in time? Could we visit the past? Physics does not clearly forbid it. But paradoxes arise. What happens if you prevent your own birth? Most physicists suspect some law prevents true time travel, but that law has not been definitively identified. Time travel remains in the realm of speculation and science fiction. Its possibility is neither proven nor ruled out. We do not know if consciousness is unique to biological brains. Could a sufficiently complex machine become conscious? Could artificial intelligence develop genuine inner experience? We cannot even agree on how to test for consciousness in systems unlike ourselves. If consciousness is a product of information processing, it might arise in any substrate. If it requires biological neurons, machines might never be conscious. The question touches philosophy, neuroscience, and the future of technology. It remains unanswered. The relationship between mind and brain remains unclear. We know the brain is essential for consciousness. Damage to the brain affects the mind. But how does physical matter produce subjective experience? How do neurons create the feeling of redness or the taste of sweetness? This is called the hard problem of consciousness. Explaining the correlation between brain and mind is one thing. Explaining why there is experience at all is another. The relationship remains one of the deepest mysteries in science and philosophy. We do not know whether reality is fundamentally mathematical. Some physicists and philosophers argue that mathematics is not just a tool for describing reality. They suggest that reality itself is mathematical. If true, the universe is not merely described by equations. It is the equations. This is a bold metaphysical claim. It cannot be tested directly, but it raises profound questions about the nature of existence. Is the universe made of matter, or of mathematics, or of something else entirely? The question remains open. We do not know what happens to consciousness at death. Consciousness ceases when the brain stops functioning. But what exactly ends? Science can describe the physical processes of dying. It cannot address what, if anything, persists afterward. This is not a question science can answer, but it is one that humans have always asked. The boundary between life and death, between consciousness and its absence, remains the most personal mystery of all. You have just traveled through over 100 of science's greatest mysteries. Questions that stretch from the cells in our bodies to the edges of the universe itself. Each one is a reminder that for all we have discovered, the world remains deeper, stranger, and more beautiful than we can fully grasp. Think of what we have touched tonight. The hidden spark of consciousness. The riddles of aging and memory. The secrets carried by oceans beneath icy moons. The timeless puzzles of stars, storms, and the fabric of reality itself. Some of these questions may be answered in your lifetime. Others may remain mysteries for generations. And still others may never be solved at all. But that is part of the wonder. To live in a universe that still holds so much unknown is to live in a universe filled with possibility. Every unanswered question is an open door. Every mystery an invitation. The fact that we do not yet know keeps science alive, keeps curiosity burning, and keeps us leaning forward into tomorrow. And as you lie here now, letting the weight of these mysteries drift across your mind, notice how gently they carry you toward rest. Like the slow rhythm of waves on a shore, the questions themselves are soothing. They do not need answers tonight. They only need to be held lightly, like starlight scattered across a dark sky. So let your breathing fall into rhythm. Let your body grow heavy. Let your thoughts soften. Imagine yourself floating through the mysteries we have explored, passing by them as if through constellations in the night. Questions above, questions below. A galaxy of wonder all around you. And you at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace. There is nothing left to do tonight. No answers to chase. No puzzles to solve. Just the calm certainty that mystery itself is a kind of lullaby. One that will carry you gently into sleep. Sweet dreams. Thank you for joining me on this journey through the unsolved mysteries of science. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the cosmos. There are more wonders waiting. More galaxies. More stars. More mysteries to drift through on quiet evenings. Rest well. And may the stars keep you company through the night. This has been Drowsy Discovery. Good night.